So in this talk, I want to show you the new class of materials called meta-crystalline materials that not only have a very high strength to work in very demanding environments like metals or ceramics, but also have the ability to adapt and evolve like materials created by nature. So the question is, how can we develop such amazing material as we wish? Sorry, I'm trying to move the next slide. Here we go. Yes, so the question is, how can we develop such amazing materials? That's where we can learn from nature. So nature is fantastic in creating materials that can evolve and take all surrounding resources to grow and adapt to the changes in environments. However, most of biological materials, they don't have a high strength like metals or ceramics, as I mentioned before. To work in very extreme conditions, for example, in high temperature, like in rocket engines. So that could be amazing if you have a new class of materials that have high strength to work in very demanding environments, but also have a responsiveness like biological materials. That sounds fiction, but actually that based a lot on science. And before I said further, I want to raise that 5 challenges we want to meet if we want to develop a material that high performing, but also behave like nature. So the first challenge is we need to be able to program the strength as we want. We want to get material to get specific strength, and in particular when they transform, we want them to have a new strength that can meet the new demands. And second challenge is the material is able to store and communicate information within inside them, and if they want to interact with environment, they need to be able to sense and take some action. When they take some action, they need to be able to calculate, computing information, and take some action, including the transformation, morph to different morphology. And when they interact with environment, they need to be able to take feedback and able to self-optimize and learning from their actions as well. And that's the 5 challenges we want to set right in the beginning. So how can we do this? How can we make material with very high performance and ability to evolve and adapt to environments? That's where we can leverage our expertise and knowledge in 2 very different approaches. One is our dream in developing invisibility cloaking materials to make an object invisible to the light. Another is a secret also found in the way we develop high strength alloys, like in aero engines. Now, look at our dream. We want to wear a cloak that can make us invisible to the light. So now if you look the way why an object is visible to the light, if you shed a light to an object, the object will reflect the light, and by doing that, the object is visible to the light. Now, if you cover the object by a cloak, and if assume we have ability to engineer the building block inside the cloak at the length scale of nanometer with the same length as the wavelength of the light, and that building block, if you arrange them in a clever way, they will interact with the light and guide the light go around the object. And by doing that, they will make objects invisible to the light. And that's the important thing. We need to be able to tailor the building block. And if you can able to do that, you can get the functionality we want, including the programmability. And that secret also shared in the way we develop high-performing metals and ceramics. If you look at any piece of metal, for instance, you take that from aero engine and you have a powerful microscope, you could see inside a metal would have many grains of crystals. That's what you see in this micrograph here to show us different colors represent for different grains. And the length of the size of the grain is almost the same size as the diameter of our human hair strand. And inside each grain that consists of billions of atoms, and atoms arranged in very ordered ways. That's called crystal lattice. First, we see here's one example of crystal lattice. Atoms located at the corner and the side face of a cube. And the arrangement of atoms, in most times, is still the same. However, the way they're oriented in space is different when we cross from one grain to the other grain. So that arrangement of building block governs the strength of the alloys and ceramics. And that's the secret. Now, if you want to understand further, now just take a piece of single crystal and you stretch them and you measure how much stress you need to pull them apart and how much extension they can bear before they fail. So that is the extension is represented by strain, and the force, how much force or stress is on the y-axis here. And in the beginning, you see the relationship between stress and strain is linear. It's similar like when you stretch a spring. Beyond a certain point, that's called yield point, you see the internal defect inside the crystal start to move, and that causes the loss in strength. So you see that drop in strength, and that happens repeatedly. That leads to very unstable deformation behavior, but also low strength as well. However, if you have a same specimen, but that made by an aggregate of crystals, you see the behavior now so much different. You have a higher strength, and the material become stronger and stronger during the deformation. And the collection of grains that lead to the higher strength, that's one of the key principal strengthening mechanisms in developing high strength alloy. That provides us ability to design any strength we want. And that is what we are doing at Imperial College. My research group, guided by the science of metals and also other materials classes as well. And we combine with advances in manufacturing, in particular 3D printing, and in other words, commonly known as additive manufacturing as well. And by learning from the way our dream to develop invisibility cloak materials, we understand if we are able to design a building block and we arrange the building block in novel way, we can get an artificial crystals that are lightweight because we extract most of the material away, and we can achieve the strength we want. And also with the way we manipulate the building block, we can make materials smarter as well. So here, as I said in the beginning, we need to achieve, or we need to meet the five or address the five challenges. The first challenge is ability to program the strength, and that's where we learn from the strengthening mechanisms in developing high-performing alloys. In here, we design a building block, and we mimic or we create artificial single crystal, and the behavior of single crystal is very much similar to the behavior of the real natural single crystal. And we also see a drop in strength and unstable deformation behavior. When we created an artificial polygrain crystals, you see the deformation behavior now is much stable, and we can get higher strength. And that really depends on the way we arrange the building block inside the artificial crystal. We can get even higher strength if we want. So we can program the strength we want. And that's the way we can meet the first challenge. The second challenge, as I mentioned, is the material need to be able to store information and communicate information inside them. So that is the way we go back to the way we design the building block, and we arrange the building block in 3D space. First of all, in this video, you see we created artificial polygrain crystals, and we arrange them to specific location, and with that we can embed information. We can dictate how the material behave under the compression, and they deform in a specific way as we designed. And the important thing is, with the way we arrange the building block, we can ask them to communicate in given way, and with that we can broaden our definition of invisibility. So first of all, if you have an impact force impact on this material, And with the way we design the building block, arrange them, we can direct the force, we can make the force transferred and directed inside material along specific way. And we can avoid certain location to make that location invisible to the force. So that can improve our protection in case we want to protect any object inside the material. And that's the way we can tackle the second challenge. The third challenge, as I say, if you want to make material evolve, they need to understand how the environment, the surrounding changes. And that means material can sense and then they can take action. Certainly, we can use the sensor, we can embed sensor or actuator inside material. But the more clever way is we can use the functional materials to fabricate our artificial crystals. First of all, in this video, you can see a material that can sense the changes in the external magnetic field. The reason for that is because people aligned the micromagnet inside this 6-leg material in specific way, and when we manipulate the external magnetic field, the legs can respond in different way, and with that the material can wrap around a medical pill and rolling and go to the site of delivery and then release the pill. And with that material can behave like a robot. So that would be fantastic, because we do not need to use any actuator or motor, or do not need to provide any like electricity to the material. And the fourth challenge is also material able to compute and sensing and take some evolution, like a transformation or morphing. So that also where we can learn from crystals as well, from nature. So one class of crystals is called the shape memory alloys. They have a fantastic functionality. They can have a two-way morphing when we heat it up and when we cool down. First of all, in this video, show us about the artificial metallic flower that can open when we heat it up and closes when we cool it down. The reason for that is lie deep down inside the shape memory alloys. The shape memory alloy have two crystal structures. One is called austenite, that only present at high temperature, and another crystal phase is called martensite, present at room temperature. So when you deform martensite at room temperature, it changes the shape. And now, if you want to return the original shape, we first need to heat it up, and the deformed martensite we transform to austenite, and when you cool it down, it will transform back to the original undeformed martensite. And by doing that, the shape memory alloy able to recall the original shape. That's fantastic phenomenon we see at atomic scale. Now, how can we translate that knowledge and that phenomenon from atomic scale to millimeter or even meter scale? That's where my research group at Imperial play a role here. We use advanced computer software to design an unit cell, and that utilizes a phenomenon in structure called buckling, and we able to transform back and forth between two stable configurations. And with each configuration, they have a specific strength, and we arrange that building block in 3D space to create an artificial crystals able to transform back and forth depends on the loading conditions. And this material, you can see we remove most of solid material inside, so that the artificial crystal is very light and with a specific strength as we design. And you can see that can open a variety of applications, for example, in transportation. Now we are facing global challenge in reducing the CO2 emissions. And with that, one way to tackle that is to reduce the weight of vehicles, and by doing that, we can increase the fuel efficiency and reduce the CO2 emissions. Now, if you apply that kind of artificial crystals inside cars, in particular in front of cars, we have a crumble zone. And the impact energy can activate the transformation from one configuration to the other configuration. The material can absorb energy, protect the passenger and the driver inside, while after the impact, the material can recall the original shape, and with that we can reduce the cost of repairing, for example. And the morphing also and evolving materials can also open opportunities in improving the well-being of our society. For example, here's one application we are working with children is to develop adaptive artificial hip. Hip can evolve and behave like a natural bones. So one problem with artificial hip is they cause stress shielding, and that means that inhibits the regrowth of our own natural bones. And that means it will degrade, the bone of the patient will degrade over time. If we want to promote the regeneration of the bone, we really need to design our artificial hip become less stiff, or in other words, it's more compliant. And with the way we can tailor the stiffness by arranging the building block, and the artificial hip can evolve thanks to the morphing in particular with the evolution, regrowth of our natural bone. And hopefully after over a few years, the natural bone will regrow and the artificial hip disappears, and the patients can have their own bone back. So that is going to be open quite a lot of promising future. And the ability to develop morphing and sensing and responsive material could open also opportunities in other applications as well. So one of that is to develop more resilient infrastructure. So we can design shelters that can transform, change in different morphology in response to natural disasters. For example, in flood situation, for example, the shelter can self-elevating to protect the people inside the shelter. But also when we downscale that, or even upscale, we can design robotic flying vehicles like drones. They can fly and behave like a bird, for example. And as I showed you before, ability to absorb energy and redistribute energy as we want, that will help us to improve the protection of our personal protection device, for example, the helmet. That is in 5 years. And if we think a little bit further in 10 or 15 years, go back to our dream to develop invisibility cloak materials. Now, as I mentioned before, we can broaden the definition of invisibility. We can make an object invisible to different signals that could be acoustic wave or seismic or elastic mechanical wave. We can use material in our city to minimize the noise pollution. We can make city more quiet. That will improve the well-being of people in the city. But also, when we can make a materials that become invisible to more energy wave, like a seismic wave, we can protect an important area. We can deflect the seismic wave away from important areas, for example, cities or important buildings, for example, like a nuclear power plant in case of earthquake, for example. And with advances in nanofabrication, we can go back to our dream, develop invisibility cloaking materials that are invisible to the light, and that really where we need to engineer and tailor the building block at nanoscale. And that is the roadmap for the future, in particular with the foundation I present in the previous slides. So we develop artificial crystals with high strength and lightweight and ability to adapt. So we see that's why variety of application in transportation, and increase the resilience of our infrastructure to natural disasters as well. So in 15 and 20 years, by 2040, we can integrate all functionality. I will show you that's very possible to use what we have learned so far, inspired by nature. We can develop intelligent materials that can learn and respond better to the surroundings. And that would help us to improve the health of our society, the well-being of our society, and the future which will become more autonomous, that help us to explore in the different world, different areas where human could not easy to access, or the area where it's very dangerous and unhealthy to the human. We can send material behave like a robot, help us to build a satellite, or help us to explore different locations, different worlds. And that is my vision in 2040. By learning from nature, we can design material that can adapt to the environment, can compute and sense and learn. And by doing that, they become smarter and more intelligent, help us to better to adapt with the change in the future. And with that, I want to thank you for your attention, and we'll be happy to answer any questions.
Thank you so much, Son. It was extremely interesting to hear how you're creating a new class of materials that almost become like living and can help us address things like climate change and health care. I think we can see that there are loads of applications, really interesting future applications. So I had a couple of questions. So first, shape memory materials have been around for a long time. So what has really enabled this step change to happen?
Yeah, thank you, Maria. That's a very nice question. I do agree that shape memory alloys already present for a long time, but that's based on the intrinsic phenomenon at nanoscale or atomic scale. And the novelty of our approach is we can enable the transformation at millimeter and centimeter scale, and it doesn't need to have an intrinsic shape memory alloys. We can apply this approach to any kind of other materials, and actually we use just normal polymers, it's normal metals, and enable the transformation. So we can upscale to larger infrastructure buildings, for example, and we can enable the transformation with the available resources. Do not need to use fancy shape memory alloys.
Fantastic. And I think this follows on one of the questions for the audience that came in during your talk, which is how applicable is it as a construction material? Can you use it today as a construction material?
Yeah. So that's very much, we just use the normal materials, just normal metals, and also, like a scaffolding structures, more stick model, and we can enable the transformation. Recently, we need to do a more clever way, because we need to build the right building block and then arrange them in specific way. And with the normal, existing construction materials, we might need to embed some kind of actuator, because they don't have like a magnetism or shape memory functionality of the intrinsic materials.
So what is the largest structure that you have enabled this material to work in so far?
Oh, that's a very good question. That very much is limited by our capacity in fabrication. So because we use 3D printing to fabricate our design, so basically that's the bio volume of our printer is our limit. But with the advances in manufacturing, where people can use robotic arms, they can increase the scale of the build volume, that we can upscale larger. But also you can see people already apply like artificial crystals already, even they are not aware of like a scaffolding structures, for example. It's a very simple form of artificial crystal, single crystal.
Fantastic. And a question here from Emily Wheel. There are so many exciting applications for this. What do you think might be the most promising opportunity for this technology early on?
Yeah, that's also a very good question as well. The future is quite promising, and because we not rely on the properties of the intrinsic materials, we can apply the approach to any kind of materials and particularly in structural applications. So in the near future, I think the most promising could be in transportation, because we have a strong demand in reducing the weight, and not when we reduce the weight, we need to think about it still need to have a strength as we use heavier materials, and also ability to absorb more energy to make the passengers and the drivers safer. So that is in near term future, I think, in transportation. But also a little bit further could be in the healthcare application, because we can make artificial like a hip or some other device can able to transform. So actually, we are working with a group of surgeons in Hammersmith to design transforming catheter, help us to manipulate the catheter tip to perform some surgery inside patient body.
Fantastic. So Ben Lawrence has a quite good question here. And so 2 years ago at the Tech Foresight conference, we had Dr. Conor Mayan speaking about 4D printed polymer material. How much of a crossover between these polymers and is there between these polymers and these meta-crystalline materials?
Yeah, thanks. That's fantastic questions. Certainly, we have some overlapping between 4D, 3D printing and this approach. But 4D, 3D printing more focus on manufacturing, and we focus on design of material, and we use 3D printing to realize our design. So that's the common is we use 3D printing to realize our design. But actually, if we have another manufacturing route, we can fabricate the design we want. We do not need to use 3D printing. So actually, we buy a lot of like rods, and we arrange them, we bond them together either with welding or just use them not to bond them together. And with that, we also can able to realize our design. And with 4D printing, you still need to use the functional materials. Material need to evolve because 3D printing could not make material evolve. That means, and this one, I mean, our approach is different. Most of the case, we do not need to use fancy materials. We can use normal materials and make them evolve.
And I guess the cost goes down as well.
Yeah. I mean, if you think about the cost for chip memory alloys, it's very expensive compared to other alloys, other metals. Now, if you do not need to use chip memory alloys, use just normal metals, which is much cheaper. And fabrication also easier, because to fabricate chip memory alloys, we need to control the chemical composition very carefully, because of the range they have the chip memory functionalities is very narrow. Anything out of that range, the material lost its functionality.
I think it's quite interesting, because I remember in that talk we were talking about the two-way morphing, and that was more of a dream of being able to do something like two-way morphing, which you can already do with your class of materials that you've developed with your group.
Yeah, that's absolutely. Just we need to combine our expertise in different disciplines, from structures, from mechanics, materials, and also art as well. So actually, we learn a lot from art, kinetic sculpture that enable the sculpture behave like a living animal. So that's where we learn from.
Fantastic. I think we'll do one question, and then we'll move on to a very, very short roundtable conversation, as we don't have, we're running a little bit behind. So the last question is from Nick Rimmer, where he asks, are there other manufacturing techniques that could be used rather than 3D printing? And I think you actually sort of have answered this already.
Now we're buying a lot of kind of wires of metals, and then we just weaving the way we can bond them together. So no need to be kind of physical bond, like a welding to join them together, but also we can use knot, for example, or just the way they support the other, and they can form a building block in regular way. Certainly there's a limitation with that, because with 3D printing, you can make much more complex. But depends on application, and also depends on the constraints in finance. We can use just normal, existing manufacturing approach to fabricate the design.
Fantastic. Thank you so much, Son.